So now we continue with how to draw the zero sequence networks of transformer and find what is the equivalent zero sequence reactance. So you can observe all the primary windings are solid grounded, secondary solid grounded, here secondary reactance grounded, here secondary isolated grounded. So now we draw the zero sequence network. So you represent the series switches, shunt switches, series switches, shunt switches. How much this one XT0 per unit. Similarly, draw this format here, the configuration. Now we will check further which switch will be closed on which side. Now observe, both windings are connected in star. So we operate only series switches, please. Now solid grounded. For solid grounded, close the series switch by means of a fuse or Xn per unit is 0. Secondary also solid grounded. So close the series switch with a fuse or say Xn per unit is 0. So what is X0 equivalent per unit now? By default you travel through XT0 per unit. And what about the remaining path? Very simple and important. You travel through the switches we have operated. So we have operated the series switches. So you travel through those series switches. How much reactance? 0. There also 0. How much you get now? XT0 per unit. Now check the second question. Solid grounded. Primary is solid grounded. Close the series switch with Xn per unit 0. And now secondary is reactance grounded. So you close the series with how much? 3Xn per unit. Close the series switch with 3Xn per unit. So how to find what is X0 equivalent per unit? By default you travel through XT0 per unit. Then fuse. And here 3Xn per unit. So I am simplifying how much now? XT0 plus 3Xn per unit. Now solid grounded. So close with a fuse. Xn per unit 0. What about secondary? Isolated neutral. So series switch open, or you say xn per unit equal to infinite. So what about x naught equivalent per unit? By default you travel through xt naught per unit. Then the switches you have operated. So how much you get? Infinite. How much you get? Infinity here. So x naught equivalent per unit is infinity. So this regarding the first three questions. Now the next three questions. Now the primary is isolated grounding. Primary is isolated grounding. If primary is isolated grounding, what about this side? Xn it is infinite. So primary is isolated grounding. What about these switches? Must be, if the primary is isolated, switches must be opened. So what about the xn per unit now? Isolated means you know that xn per unit is infinite. And then what about x naught equivalent? By default you write xt naught. Then you travel through the switches you have operated. Here 3xn per unit and infinite. Here lastly it is infinite. So this is how you find x naught equivalent per unit. How much they are equal to? Infinite. So this is how you analyze the next three questions of the zero sequence networks of transformers. Now you formulate the next three. Now make the reactance as, make the primary solid neutral, reactance neutral. If the primary is reactance neutral, what about the reactance now? Close the series switch with how much reactance? 3xn per unit. With how much reactance? 3xn per unit. So what about this side now? It is 0 xt naught per unit, 3xn per unit. Here also 3xn per unit. And there also 3xn per unit. So we have to find out what is x naught equivalent now for these three. So here it is xt naught plus 3xn per unit. Here xt naught plus, and don't write 6xn per unit please, the maximum finite zero sequence reactance is xt naught plus 3xn. The maximum finite equivalent per unit reactance, the maximum finite equivalent per unit reactance, how much? xt naught plus 3xn per unit. What about this last one? Infinite. So why only this 3xn? Because it is the maximum finite zero sequence per unit equivalent reactance. So the maximum finite zero sequence per unit equivalent reactance. So this is how you evaluate these last three questions. Now you make all the primary windings delta. Make all the primary windings delta. So you have to by default operate shunt switches. You have to by default operate shunt switches. And so what to do with the shunt switches? Only one step. For any delta configuration, close the shunt switch. With how much reactance? Xn per unit equal to 0. Nothing but a fuse. With how much reactance? With Xn per unit equal to 0. So what about X naught equivalent per unit? By default, you have xt naught per unit. Then the switches we have operated, series switch, here shunt switch. So this is the path to be considered to calculate X naught equivalent per unit. How much? xt naught per unit. Here by default you travel through xt naught per unit. Then first 3xn per unit. Then xn per unit 0. So how much you write? xt naught plus 3xn per unit. What about now? You travel through xt naught per unit. Here infinity, here 0. So how much you get? X naught equivalent per unit, it is infinite. So this is how you calculate the equivalent per unit zero sequence reactance. Now we have the last 13th configuration where you represent both windings in delta. Where you represent the both windings in delta. So when both windings are connected in delta, how to analyze now? By default you represent the configuration xt naught per unit, shunt switch, here also shunt switch. So how to analyze now? Delta means close the shunt switch. With how much reactance? With Xn per unit 0. with Xn per unit 0. And how to find what is X0 equivalent per unit? You travel by default through XT0. And the switches we have operated. So here shunt switch, here also shunt switch. And adding this total, how much you get? XT0 per unit. You get XT0 per unit. So this is the path you have to travel to calculate X0 equivalent per unit. So please once again evaluate these last 13 configurations regarding the zero sequence networks of transformers. Now we check how to draw the sequence networks of an alternator operating under no load conditions. So you consider an alternator and each phase how you represent by the source and the reactance connected in series. By the source and reactance connected in series. No load means you represent initially the currents IR, IY, IB. And now you represent the reactance grounded, so Xn per unit is 0. So here XR per unit, ER per unit. Here EY per unit, XY per unit. EB per unit, XB per unit. Now for this synchronous generator operating under no load condition, we have to draw the sequence networks and accordingly you find the equivalent reactances. So now first we check how you draw the positive sequence network. How to draw positive sequence networks. We know that positive sequence network consists of positive sequence generated EMF ER1 per unit. We have proved earlier in 1 hour back. A positive sequence network consists of positive sequence EMF generated ER1 per unit. So represent this one. How much ER1 per unit and how much it is further equal to ER per unit. And here XR1 per unit, say the positive sequence current IR1 per unit. So you have the phase and neutral. So between these two you find out what is VR1 per unit. So what will be the VR1 per unit now? Total is ER1 per unit minus the reactive voltage drop IR1 into XR1 per unit. And what is the opposition to flow of positive sequence current XR1 per unit? You also name it as X1 equivalent per unit. So what is X1 equivalent per unit? Equivalent per unit positive sequence reactance. So what you call it as? The equivalent per unit. One is positive, the positive sequence reactance. Next is the negative sequence network. So how you draw the negative sequence network? Already we have proved the negative sequence EMF generated ER2 per unit equal to 0. So ER2 per unit is 0. So represent like this. You have XR2 per unit. Here say the current flowing is IR2 per unit. Now you find what is the terminal voltage? VR2 per unit. So what is VR2 per unit? We say ER2 per unit minus J IR2 into XR2 per unit. So ER2 is 0 minus J IR2 per unit XR2 per unit. What is this opposition to flow of negative sequence current? You name it as X2 equivalent per unit. What is this X2 equivalent per unit? The equivalent per unit negative sequence reactance. So the equivalent per unit negative 2 is negative sequence reactance. So equivalent per unit negative sequence reactance. Now lastly, we have to draw the zero sequence network. Now here we develop the generalized equation. For developing the generalized equation, you consider reactance neutral 3xn per unit. So what should be this current? IR naught. If reactance is 3xn, mention the current IR naught. If reactance is only xn, mention the current as 3 IR naught. We have written them in the previous session. And now you know that zero sequence generated source 0. So positive sequence generated EMF source ER per unit. Negative sequence generated EMF source ER2 per unit 0. Zero sequence generated source ER naught also 0. So you represent its reactance and no source here. So ER naught per unit is 0. What about here? XR naught per unit. And what about the current that is flowing? IR naught per unit. Now most important point, IR naught per unit also flowing through where? IR naught per unit is also flowing through 3xn. Is also flowing through where? 3xn. So we have to check what is VR naught per unit. So how you write? ER naught minus J IR naught into XR naught. How much ER naught is? 0. Minus J IR naught per unit. Now it is not only flowing through XR naught but also flowing through 3XN. So it is X naught equivalent per unit. XR naught plus 3XN per unit. So what you call this X naught equivalent per unit now? So what is the reactance offered to the flow of zero sequence current? XR naught plus 3XN, or you say X naught equivalent per unit. What is X naught equivalent per unit? It is the equivalent per unit zero sequence reactance. This formula of X naught equivalent is most important place. How much it is? XR naught plus 3XN. XR naught is the zero sequence reactance of alternator of R phase. 3XN is ground neutral or connected by reactance neutral. So what is the reactance? 3XN per unit. So this is how you draw the sequence networks. For positive sequence network, negative sequence network and zero sequence networks. Now you know that the first component in a power system network is generating station. And how you represent generating station electrically? That is the alternator of generating station electrically by a voltage source. So now we have to check what are the reactances offered by alternator, that is the reactance offered by alternator before fault and immediately after occurrence of fault and immediately after few cycles after occurrence of fault. So all those points we discuss now. So the topic is reactances offered by the alternator before, during and after fault. So reactances offered by alternator before, during and after fault. So first we know that an alternator consists of three windings in parallel. Consists of three windings in parallel. Armature winding, field winding, damper winding. So what is the equivalent reactance now? The parallel combination of all these three, XA, XF, XDamp. And now you say that a fault has occurred. Immediately after occurrence of fault, what is the reactance offered by alternator parallel combination of all these three. That reactance offered by alternator immediately after occurrence of fault is known as subtransient reactance. So first we write about that. Subtransient reactance. How to denote? XD double dash. How you define? It is the reactance offered by the alternator immediately after occurrence of fault. Immediately after occurrence of fault. So what will be that XD double dash per unit now? The parallel combination of all the three reactances here. And how long this subtransient duration exists? Subtransient duration exists for only 2 cycles. And what happens within this subtransient duration? Damper winding is disconnected. Damper winding is disconnected. So you mention now, during subtransient duration, that is 0 to 2 cycles, damper winding is disconnected. If damper winding is disconnected, what you will have? Only XA and XF. And what is the reactance offered by alternator after 2 cycles of fault occurrence? You name it as transient reactance XD dash per unit. So what is transient reactance? Reactance offered by alternator not immediately, after 2 cycles of fault occurrence. You name it as transient reactance. So what is transient reactance? It is the reactance offered by alternator after 2 cycles of fault occurrence. So it is XD dash per unit. And how long this transient duration exists? For another 2 cycles, that is up to 2 to 4 cycles. And what happens during this transient duration? Field winding is disconnected. Field winding is disconnected. So now we mention that during the transient duration, that is 2 to 4 cycle, the field winding is disconnected. If the field winding is disconnected, you are left out with only XA per unit. So what happens? XA per unit means it is the steady state reactance. You name it as direct axis reactance XD per unit. Direct axis reactance XD per unit. That is, reactance offered by alternator after 4 cycles of fault occurrence. So how much XD dash per unit? XD is XA only. So how you define? It is the reactance offered by alternator after 4 cycles of fault occurrence. So XD how much? Only XA, or it is the steady state. So this is regarding the 3 reactances offered by alternator. First one is subtransient reactance immediately after occurrence of fault. Next, transient reactance after 2 cycles of fault occurrence. Next, direct axis reactance after 4 cycles of fault occurrence. Now, among these 3, which is the minimum? Suppose you verify each one is 3 per unit. If each one is 3 per unit, how much here? 1 per unit. 1.51 unit, 3 per unit. So what is the answer you get by comparing the results? XD double dash per unit less than XD dash per unit and less than XD per unit. So these are the reactances offered by alternator before fault, during fault and after fault. And all the switchgear devices, the circuit breakers, relays are designed to clear the fault within 5 cycles. Otherwise, the system becomes unstable. Otherwise, the system becomes unstable. So these are the reactances offered by alternator before fault, during fault and after fault. Now we solve the questions based on the sequence networks. Is asked in one of the IS question papers. A 3-phase transformer having 0 sequence impedance Z0 has 0 sequence network as shown in the figure. The connections of its windings are, figure is like this. Is primary, secondary, here reference bus. So here you check, shunt switches are closed on either side. When you close the shunt switch, when the winding is connected in delta. So how the connections of the windings are? Delta and delta. It is in delta and delta. Next question. These also from an IAS question paper. A three-phase transformer having zero sequence impedance Z0 has zero sequence network as shown in the figure. The connections of its windings are. So instead of XT0 given as Z0, but primary side you verify shunt switch is closed, series switch is closed. Verify secondary side, shunt switch is closed. Secondary side, the shunt switch is closed. So primary switch closed like this means primary winding is connected in star with grounded neutral. Star with grounded neutral. What about secondary? Delta. So what about primary? It is a star with grounded neutral. And what about secondary? It is delta. Now we solve this next question. And this from a GATE question paper. For the network shown in the figure, the zero sequence reactances in per unit are indicated. So now we have to calculate the zero sequence driving point reactance of node 3 is. So the network given is like this. We have step-up transformer line, further another generator, for alternator Xg0 is 0.1, this bus 1, bus 2, bus 3, delta, and here solid grounded. Xt0 is 0.15, XL0 is 0.05, Xg0 is 0.5. So we have to calculate with respect to node 3 here. You have to calculate with respect to node 3. So we draw the zero sequence network now. For alternator, represent Xg0. What about ER0 per unit? 0. Here only given Xg0 per unit. But here we have solid neutral. If we have solid neutral, 3xn per unit is 0. Solid neutral, so xn per unit 0. In general you write Xg0 plus 3xn. Now transformer. Primary we define by default Xt0 per unit. So represent the configuration and accordingly you close or open the switches. And so how much now? Primary is in delta. If primary is in delta, close the shunt switch. How much Xn per unit? 0. Secondary is solid neutral. So how much Xn per unit is? 0. So here you come across bus 1 and here bus 2. After that we have transmission line. What is the reactance of the line given? It is mentioned in the question 0.05. So XL0 per unit. Next we have the bus 3. Further alternator. Again solid neutral. So you close the series switch. You close that Xn per unit 0 means a fuse. Next Xg0 per unit and no source here. Zero sequence network. ER0 per unit is 0. So where you will find out what is the X0 equivalent per unit, you find out where you are asked to check at bus 3. So here we have to calculate X0 equivalent per unit. Calculate X0 equivalent per unit. So I repeat how you draw this one. First alternator, ER naught per unit 0, Xg naught is given solid neutral 3xn 0 closed by a fuse. Then transformer primary delta close the shunt switch Xt naught per unit as usual. Secondary solid neutral close the series switch with Xn per unit 0. Next we have a line XL naught per unit, again alternator Xg naught per unit, ER naught per unit 0, solid neutral, so Xn per unit 0. So how to find what is X naught equivalent per unit? Find the reactance to the left side, right side. That equivalent gives you X naught equivalent per unit. So what is it you are having to the left side? XL naught. You travel through the switches we have operated. So series switch and by default XT naught. You have operated shunt switch, so you have to travel like this. So this is the path you consider to calculate the reactance to the left side. So what you have to the left side? XL naught, Xn naught per unit 0, further XT naught per unit, again X naught, Xn is 0. What about to the right side? Xn per unit 0 and here Xg naught per unit. How much XL naught? 0.05, XT naught 0.15, Xg naught is 0.2. So you get 0.2 and 0.2 in parallel. How much it is? 0.1 per unit. So simplifying, you get the answer as 0.1 per unit. And many more questions on these sequence networks. We continue after this break. First question is by Rachel. Explain why in unbalanced condition we consider 3xn. Now in unbalanced condition, what is the voltage IN into Xn? IN, how much you got? 3 IR naught. If you say zero sequence current is flowing, what should be the corresponding reactance? 3xn. That is the reason. And one more question by the Rachel. Why we analyze an alternator operating under no load condition? Is it because if sudden loss of line occurs, then what is the effect on alternator? Yes, you are correct. Next question is by Gaurav. In star system, if we use resistance grounding in place of reactance grounding, then will it affect the system in case of grounding of generator and both are mode? Yes, definitely it affect. We solve our 14th question based on your concept. Next question is by Rachel. What is the value of Xn in practice? Now we design Xn or according to 3xn, we design 3xn only please. And by default it will be some 0.05 for alternator and 0.6 for lines, these values. Next question is by Tanmay. Why do we connect 3xn for zero sequence only? Because ground to neutral, when IR naught is flowing, for reactance neutral, the reactance offered is 3xn. You please refer the earlier sessions at the beginning of the middle of this today's session. Ground to neutral current, say IR naught is flowing. If it is reactance neutral, the reactance is 3xn. Or you check here, 3xn. Here it is the zero sequence current flowing, so show it in zero sequence network only, but not in positive sequence and negative sequence. Next question is by Rachel. Zero sequence currents have no phase sequence, but you represented them as parallel. Not parallel means no phase sequence, right? Parallel means no phase sequence. Next question is by Vishwam from Agartala. Why damper winding is disconnected in subtransient duration? Why field winding is disconnected in transient duration? Only in order to decrease the fault current magnitude place, no other reason. Next question is by Rachel. During subtransient period, the reactance becomes very low, so current is maximum. Yes, your statement is correct. Then it will affect the machine place. Reactance less, more short circuit current it will affect. How to make it not to affect? Use circuit breakers and relays to operating subtransient duration. Next question is by Rachel. What is driving point reactance mentioned in the question? The meaning of the word driving point is you measure the voltage and current at the same node. You measure voltage and current at the same node.